Hello, and welcome to the first part of section 7.5. I'm going to talk about area of a surface of revolution. I'm going to go over the derivation of the formula first. I'll give you the actual formula, and then in my next video, I'll go over some examples. Now, I wrote a code in MATLAB to show you what I mean by this, by a surface of revolution. And the idea is that say that I want to, I have the graph of x cubed from 2 to 3, and I want to rotate about the x-axis. Now, if I do that, then what I'm going to obtain is something that looks like this. Let me just, this is called surface of, okay, so surface of, so this is what I get. And this is what's going to happen if I'm looking at this surface from the xy axis. But then this is what you actually get. You get a three-dimensional figure that looks like this. Now, if we were computing volume, because we did this in previous sections, computing volume, when you looked at the figure from the front, then you get a solid figure, and then that solid, if you want to compute the volume, then it's a perfect circle when you look at it from the front, and then you add all those areas all the way to the end, and you get the volume. Now we want to do something similar. We want to take this surface that we created and we want to break it down into tiny little bands or ribbons or strips that you can then add them all together. What I mean by that is, my approach is I'm going to take, say for example, instead of going from 1.75 to 3.25, let me take just a little strip. Let me go from, say, 2.5 all the way to 2.55, so 2.55. And if I do that, what I get is, well, this, okay? I get a little strip that I'm rotating about the x-axis. So let me take this to my iPad and then I'll continue the explanation. Now, the same way that in order to compute volume, we added all the areas. So the same way we compute in volume by adding all the areas and then multiplying by the thickness of the areas, now we're going to compute surface area by adding all the circumferences, right? Circumferences times the thickness of the little circles that we have, okay? So what I mean by that is that now, here we go, we can compute, if I split my region into n subintervals, and then this is my xi, and I draw a little circle here, then the circumference of this circle, well, we know it's 2 pi r. Well, r is just the height of the height here, right? It will be just the function evaluated at my xi, which I'm going to call xi star for you to know that at that xi star, it's anything in that little subinterval, okay? Because I look at this and I know that if I decide to substitute the left endpoint, this radius will be smaller than if I substitute the right endpoint, like I'm doing here. That will be larger. So then that xi is something in that subinterval. So what do I have so far? I know that what we're doing is what we always do in math. We take this large problem and we decompose it. We break it down into smaller problems. So surface area, we're approximating with n little circles, right? So I equals 1 to n of the circumference of each of the circles, but then notice that they have a little thickness, like I said before, okay? There's a little thickness here, so then circumference times the thickness. Perfect. Now, the circumference, as I said before, well, this is just, we have again, sum from I equals 1 to n of the circumference, which is 2 pi, and then r, well, r is just a function evaluated at that xi start in the little subinterval, and now we have to take care of the thickness, okay? Now, the thickness here is not as simple as in previous sections where it was just delta x or delta y. Notice that here my thickness, this is not the distance from one endpoint to the other one, right? This is not parallel to the x-axis. It has a little curve there, okay? Now, the thickness will be the length of this little curve here, or if you want to call it by what it is, it's the arc length. That's the reason why we went over arc length, okay? Now, in case you don't remember, the idea of the arc length was, oh, I'm going to compute this I'm going to compute the length of this curve. Imagine I take the curve and I make it something, I stretch it out. Then we approximated the curve by taking lines, okay? And then we were able to get infinitely many of those lines, therefore get the exact length of the curve, and we call that the arc length, okay? So I'm not going to go into details, but we know that then this right here, that thickness, so thickness, it's given by the arc length, okay? The arc length. And then the formula for the arc length is just the square root of 1 plus, and then we have f prime of that xi star, you square it, delta x. So I'm going to take that whole thing and write it here. It's just the square root of 1 plus f of f prime of xi star, square it, and then times delta x. So now that I have this approximation, I know that if I take infinitely many of these little strips, then I'm going to get the exact surface area. So I'm ready to turn this into my formula. So the surface area is now equal to that sum I replaced with all the little sums, with all the little subintervals, which is just from A to B. So I'm turning this approximation to the continuum, right? So the whole interval goes from A to B. Well, 2 pi is still 2 pi. F of xi star turns into f of x because now I'm taking all the x's into consideration. Root of 1 plus f prime of x, and then square it, and then delta x turns into dx. And now this is my formula for surface area, okay? This is the area that I obtain when I rotate the function f of x about the x-axis from A to B. So let me give you the formal definition. So if f is positive and it has a continuous derivative, meaning it's smooth, then the definition of surface area is, well, if I'm rotating my curve f of x from A to B about the x-axis, it's given by the integral from A to B of 2 pi f of x times the arc length argument and then dx. And then this is the notation if we use Leibniz notation. Obviously, you can also rotate this about the y-axis. So instead of just memorizing all the technique, all the different formulas, then understand where the formula comes from, which is how everything started, by noting that the surface area is the circumference times the arc length argument, and then dx or dy, depending on whether we are rotating about the x-axis or the y-axis. Then make sure that you integrate with respect to a proper variable, and make sure that your r, the radius, and the bounds are correct, okay? I hope this makes sense, and then stay tuned for the next video where I'm going to solve some problems, okay? Bye-bye.